Hello, I'm Mr. McBrien. This is TEJ20, Boolean logic. So we've already seen something interesting. We've seen that we needed an electronic switch to enable sophisticated devices. And now we have that. We have our transistor that can be switched on and off by a small electrical signal. But that's not the complete puzzle. We have to figure out how to go from that on-off that a transistor gives us to things like burglar alarms, collision detection and prevention systems in Super Mario Kart. So how do we do this? Well, the answer is we have to go back a little ways in time. In the 1850s, George Boole developed a new form of algebra. Now it's called Boolean algebra in honor of him. Now, this isn't a typo. It was 170 years ago, before the days of computers or even really electricity as we view it today. And in fact, his logic system was an interesting abstract idea until an MIT student named Claude Shannon demonstrated that this Boolean logic could be used very well in terms of building electronic circuits. So Boolean equations today use the binary number system, and they give us a very precise way of illustrating the logic of computer chips. So let's dig a little deeper then into Boolean logic. So the Boolean logic system used a couple of very simple relation ideas in order to look at sets of information. So we could look at the contents of a parking lot in terms of the AND operation. So we could look at the black cars that are contained in a parking lot, and we could look at the cars that are made in Canada in a parking lot. What's interesting here is that often we can superimpose some of those things. So there will be some cars made in Canada, some cars that are black, and there will be some cars that are both. And so if we take the AND operation on those two sets, then the overlap between those two things is our black cars and made in Canada. Now, we can also, from the Boolean system, look at the idea of OR in the same way. So we can look at the black cars that are in the parking lot, the ones that are made in Canada, and in fact, both of those sets would conform to our OR operation. In other words, every car that we'd counted gets counted as black or made in Canada. So the shaded group then is representing where that operation fits. We can also look at not or. So if we look in those terms, we can say, what about the cars that are neither black nor made in Canada? And in fact, it's all the ones that we don't count. So that seems very indistinct in terms of its correspondence to electronics until we consider the idea of the binary number system and the idea of a 1 in the binary system representing on or yes, and a 0 representing off or no. So Boolean logic can actually apply to those yeses and nos in the same way as it applies to sets. And in fact, it does, and it's a part of almost every aspect of computer electronics. So we can look at something called a logic gate that takes a signal and does something with it. So it can take an input, we usually refer to that as A or B, and it can give an output, which we refer to usually as Y or X, unless we need more variables. And remember, in binary logic, we have a 0 for no and a 1 for yes. Well, in a logic circuit, 0 volts is no, and 5 volts is high, or yes. So we can take and construct circuits that will allow us to examine the signal, the inputs at A and B, and then create an output that matches Boolean logic. So an AND gate would take and have Y be high only if A and B were high. An OR gate, Y would be high if A or B were high. This special NOT gate that we're going to construct today inverts the signal. So if a high signal comes in, a low signal goes out, and vice versa. And the rest of the gates go from there. And so there are Boolean symbols for these. He created these back in the 1850s, and we still use these for a kind of, to simplify our circuits. And we'll talk more about that a little bit in this class and a great deal in grade 12. Okay, so it can often be confusing understanding what kind of outputs we can expect from given sets of inputs. It's hard to anticipate all of these without a great deal of knowledge going in. However, something called truth tables can really help out with this. So what we can do is we can systematically document every possible output based on every possible input. And once we've populated this table, we have a very good understanding of what we can expect from our circuit. It's just a little bit of work. So let's illustrate that with an AND gate. Remember that an AND gate will give us a high output, a 1 from Y, only if A and B are 1s. Well, if you were listening closely to that sentence, you should be able to populate this truth table very easily. If A is low and B is low, then we can expect Y to be low. If A is low and B is high, unfortunately that's still a low output because we need both of them to be high. And you can probably figure out what the next output is. It's a 0. And then finally we reach the case where our output can be high. Both A and B are high, and so Y, our output, is high. So we can look at this and we can see that both inputs have to be yes to get a yes as an output. We can do the same thing for an OR gate. Remember, an OR gate, the output is high if A or B is high. Well, in this case, A and B are low, so the output is low. The next one, B is high, therefore the output is high. The next one, A is high, therefore the output is high, and we reach an interesting situation. In the final case, A and B are high. Now you might be tempted to put a 0 in here. In fact, it's a 1. There's a specialized gate for this, what's called an exclusive OR, which means A or B, but not both. So an OR gate will give a high output if A and B are high. Okay, our NOT gate, we discussed this. It simply inverts our input for the output. So wherever we see a 0, we see a 1. Wherever we see a 1, we see a 0. Okay, a NOR gate, requires a little bit more discussion. So NOR is short for not or. And this little dot here represents an inversion of our OR gate. So in our first case, with A and B 0, an OR gate would give a 0. This means that our inversion means this should be a 1. For all the other cases, the OR gate would give a 1, therefore we should expect a 0 for each one of those. And in fact, that's what we see. So this is the opposite of an OR gate. Now the fun one. Okay, we alluded to the idea that an OR gate will accept A or B or both. An exclusive OR gate is just like an OR gate, except it won't accept both A and B to give a 1. So when A and B are both zeros, we see a 0 as an output. When A is a 0, B is a 1, we get a 1. When A is a 1, B is a 0, we get a 1. And this is the case where we depart from the OR gate. In this case, because A and B are 1s, we get a 0. All right, let's try a NAND gate. So this is the same as an AND gate, except it's inverted. So for an AND gate to be high, we need both A and B. The NAND gate will be the opposite. So when A is 0, B is 0, we get a 1. When A is 0, B is 1, we get a 1. When A is 1, B is 0, we get a 1. And this is the only case we get a 0. It's when A and B are 1s, we get a 0. The inversion of the AND gate. Okay, our XNOR gate. This is an exclusive not or gate. So the easiest way to think of this, first we populate a not or, and then we invert it. So our not or gate would give a 0, would give a 1 when A or B. Always takes a few seconds to do these. When A and B are zeros, a NOR gate would give a 1, and we should get a 1. When A is 0, B is 1, this is a 0 with an NOR gate, and we should get a 0. Vice versa, the same thing. A equals 1, B equals 0, we get a 0. And this is the case where we see that case where, because it's exclusive, not or, we get a 1 when A equals 1 and B equals 1. So this is the simple inversion of the XOR gate. All right, so let's pause for a second. There are places on your note template for you to sketch those population diagrams, those Venn diagrams, the circles on your, the circles in the boxes associated with those other gates. See if you can sketch those things, and if you like, you can always work with a partner to see if you can get them. Please don't just look up the Venn diagrams from these. You will benefit from taking the time to think about them. All right, hopefully you took the time to build those Venn diagrams and they're making a bit more sense to you. But I suspect at this point you're kind of saying, okay, well, that's a lot of logic diagrams and I still don't really understand how I'm going to construct a complicated device based on such a simple operation. And the answer is that logic gates aren't all that interesting when you just consider one at a time. We put them in combination in circuits to accomplish things. And in fact, when a logic for a given situation is simple enough, we don't actually need a computer chip. We don't need to write a program in order to control devices. And for a very long time, electronic devices were designed without the use of computer programs or microprocessors. They simply were based on a basic logic circuit using these kinds of gates. Okay, so let's combine some gates together to illustrate a useful device that we can design around this idea of an OR gate. Let's imagine we're building a burglar alarm system and we want the alarm to trigger if any of the sensors go to high. So the sensor gets triggered. Maybe it's a proximity sensor or a window or a door sensor for vibration. But the signal from that sensor goes to high. And we want the alarm to trigger immediately and trigger sirens and all kinds of crazy things. But the key thing is just for a signal from our processor, from our set of gates, to go to high as soon as any of these sensors go. Remember, we don't want all of the sensors to go. We don't expect our burglars to enter through every window in our house at the same time. So we need OR gates. All right. And then we can put this in words. If any entrance sensor is triggered, a high voltage will come out of our detector device. Now in Boolean logic, this is easy to understand. We have our output is equal to the output from window 1 or the output from window 2 or the output from window 3, window 4, window 5, window 6, door 1 or door 2. If any of those go to high, our alarm goes off. So in fact, we can draw this with our gates. We can have a series of OR gates. We got window 1 and 2, window 3 and 4, window 5 and 6, doors 1 and 2. And these OR gates, the output from any one of those gates will be high if any one of those sensors goes. And then we can combine those into 2 more OR gates, and finally 1 more OR gate. And essentially what we've got is our output from Y is high if any one of these goes to high. And a portion of our truth table is here, looking at the signal Y being high if in any case except if none of the sensors have been triggered. Can anyone spot the problem with our alarm system here? I'd invite you to pause the video for a second and think about what the problem is with our alarm system as it stands right here. Well, the answer is our alarm would always be enabled. We couldn't enter or leave our house, which, who knows, in a COVID-19 world, maybe that makes sense. But we would never be able to open or close any of our windows or doors if we had that alarm system as it was. But in fact, by adding 1 more gate, we can make our alarm system much more versatile. So what we can do is we can say in our logic, a sensor has to trigger and the system must be enabled for the alarm to go off. So we add an AND gate. The output from our sensor system goes to high whenever a window or door opens. However, we have to have turned the little key to enable the alarm before the alarm can go off. If we turn the key to the off setting, E input goes to 0 and the alarm can't go off. So very simply, we've created a useful burglar alarm with just a series of sensors and a few gates. And here's our revised truth table incorporating windows, doors, and the enabled system. And we have a new expression now. So our Boolean expression, which we haven't gone into in too much detail yet, our output is equal to windows and door sensors with an OR statement between each one, and the alarm must be enabled. Okay, let's sum up. Logic gates are the basis of the modern electronic logic that we see in so many devices today. They're based on the idea of Boolean algebra. Logic gates form the basis of things like a CPU, these huge processors we use. However, they can be combined with other gates to create circuits that produce logical outputs without needing to write computer programs. We can represent the behavior of these gates using truth tables or using Boolean expressions that we'll get into later. All right, so I've included an activity for you to work on. First of all, you want to do your Venn diagrams. Once that's done, you can go ahead and build one of the gate circuits either online or using hardware, depending on what you have available. Thanks very much. Have a great night. Hello, I'm Mr. McBrien. This is TEJ20, Boolean Logic.